Alright, so I just wanted to record this, make sure this was clear for y'all. I'm just going to do an RC circuit. So here we have our resistor, a little resistor right there. It's a 330 ohm resistor, and I've got it connected to this negative terminal of this little capacitor here. So it's a 25,000 microfarad capacitor, or a 0.025 farad capacitor. I'm going to go ahead and hook it up, and as you guys will notice, let's see here, put the positive over here, we got the negative, so we'll kind of over here and connect the negative to our little power supply, and we're going to use 5 volts for our power supply. So we can see all that, but then it's like, well, if we want to see what's going on, we're going to have to hook up some volt sensors. So I'm going to hook up 1 volt sensor here to the capacitor. So I'll just come in here, and then I'm going to actually just connect this to the same terminal as the volts, or the voltage coming in from the power source. So we got that, and then I'm going to put another voltmeter in here on the resistor. So I'll come in here and put this on the positive side, and then I'll connect another lead to the negative side there. So we can see that this becomes a mess. So the point here of showing you this isn't to show you like, oh, so I'm showing you A, how it's actually hooked up, but B, this is also a friggin' mess. So one of the things we can do is, instead of looking at the actual circuit, we can look at a circuit diagram. That's again kind of the point. There's also a switch, not pictured here, over by the power supply that I'll use to connect, or to turn it on to connect everything when we're ready to go. Okay, so let's take a look here. So I pulled up a capstone, and I've got, this is the voltage across the capacitor is going to come up here. We've got the voltage across the resistor over here. We've got the circuit in either case. So we got 5 volts, 0.25 farads, and 330 ohms. It's the same circuit twice, but this one has the voltmeters attached, and this is a little bit simpler if we don't have to deal with the voltmeters. So looks like we're ready to go. I'm going to go ahead and click start recording here. Yeah, go ahead and start recording, and then I'll close my switch. And there we go. And we get some voltage increasing here, decreasing there as predicted. I'll just go ahead and run this little simulation so we can see that the current is running from the positive end of the battery through the capacitor, through the resistor, back to the battery. And as you see here, the voltage builds up on the capacitor and it decreases on the resistor. And so we can see it has this nice timing curve here, and then we can see that the voltage starts, and then starts at maximum and decreases. And eventually, it decays away to 0. So I put it at 5, so it looks like it's a little different than exactly 5. Yeah, so that looks pretty good. I'd say we've got a full charge or discharge, however it goes. So I'm going to go ahead and stop everything here. So I'll go ahead and stop that, and we can see, well, that's just what we have. So remember, with RC circuits, at first the capacitor acts like a wire, and all of the current's going to go through it, which is why all of the voltage just goes across the resistor, because it's the only thing to resist the current. But as that charge starts to build up here, I'll go back to this, as the charge starts to build up over here, it's going to start resisting that current and pushing back against it. And so then you need some more voltage on your capacitor, and as that voltage across the capacitor increases, the voltage left for the resistor will always decrease. Now there's a couple of things before we get to any little calculations I want to cover. So every capacitor is going to have a little bit of what's called leakage current, because again, capacitors should have, ideal capacitors should have infinite resistance. They'll always have some leakage current, but this one's actually pretty good. And I don't know if this is leakage current that we're seeing here because there's a voltage, or if it's just detecting 0.2 volts, because I don't think it has a resolution really of that small, but hey, who knows. So what we can do here is, let me pull up the calculator here. So let's clear that. So we've got, looks like our maximum voltage is 5.07. We'll do that times our so we know it's going to charge up to maximum, but we know one time constant should be 0.63 or 63% of the original voltage. So that means we're getting a voltage at one time constant. We should have a voltage of 3.19, so about 3.2 volts. Oh, we didn't calculate the time constant. Let's calculate ourselves a time constant. So the time constant we can easily calculate by taking the resistance, 330, times the capacitance of our capacitor, in this case 0.025. So we get a time constant of 8.25. So we've calculated both things here. So I'm going to flip over to this graph. It's just the same. This is again just the voltage across the capacitor, so we can just more easily see it. So I can come over here and click on this. Let's see here, 0.03. So it looks like it's reading 0.03 before we even get started. So okay. So it looks like that's our first point there. So we said, okay, after one time constant, so that would be 0.825. So let's get close to there. There we go. So at 0.825, we said we should have about 3.19 or about 3.2 volts. And this is what I think is important to see, because there's a lot of things in physics that it's hard to see, because again, we take the real world and we make a model on it, and then that model is what we use to make our calculations. And then we say, oh, why aren't these calculations the same as the real world? Well, we make certain assumptions when we make that model. And you know, there's lots of assumptions that happen here too, like even the resistor has a plus or minus 5%. But even with that, we can see that this pretty ideally matches exactly what theory tells us. Okay, so let's do the other one. Let's do the discharge now. So for discharge, I'm going to go ahead and take the battery out of these circuits here, just so it looks better. Stop that. See, I'm going to disconnect the battery there. I'm going to disconnect it in real life, but I'm not going to connect my switch yet. So I'm going to go ahead and start recording, and so we see that it should be doing this. So let me go ahead and flip that switch, and here we go. So now you can see the voltage on the capacitor starts at its maximum, what we had charged it up to, and it's going to decay away. And the voltage on the resistor actually is negative, and again it starts at maximum and it's going to decay to 0. Now in this case it starts at maximum because there's nothing else in the circuit, except for the capacitor, which in this case is kind of acting like a battery. But as the resistor resists, it's going to burn up that energy that's stored in the capacitor, and eventually we'll get down to 0 voltage across the capacitor and our current will stop. And so you can see both from this diagram here that the current's going in the opposite direction, and we can infer that from the voltage across the resistor here. So it looks like we're just about done, and this is what I'm saying about the 0.02. Like, I don't know why it's picking up 0.02 when nothing's happening. So that actually dropped a little bit, so maybe I just didn't wait long enough, but not going to wait long enough now either. So that's what we get, and again we can jump back over here and we'll check ourselves out a discharge curve. So again, this is just across the capacitor, and we can say, okay, well, we started here. Let's see here, 5.08. Where's the stuff start to drop? Ooh, there we go. Okay, so we started to drop there. We'll do our delta. Again, it should have the exact same delta time, the 0.825, and here we'll see that the remaining voltage is 1.86, so we can do that calculation as well. We can say our original voltage was 5.08, and we multiply that by, in this case, not 0.63, because it doesn't have 63% remaining, it has 63% gone, which would be 0.37 remaining. So we should get about 0.187 0.188. So we got 0.186 here, and you can see that obviously this is the delta V, the 3.22 is what we lost. So again, pretty dang close to ideal. If you want to take it further, you can go out like a second time constant. So a second time constant, well, we can just double this, right? 8.25. So that'd be 16 and a half. 16 and a half, somewhere. Oh, there it was. So 16 and a half, we can see it's 0.72. So we do the calculation here, we can see that our starting voltage is 5.08. And so remember that this case, instead of doing instead of losing 37, or instead of multiplying 30, in this case, remember that we're going to have to see not 37%, but it's going to be 37% of the remaining 37%. So that would be only about 14% remaining. So if we want to find 14% of this number, why did I do that? Yeah, 14% remaining of this number would be about 0.71. And so as we see here, we have a 0.72 left after two time constants. Again, we could say that part remaining, we've lost 0.86%, so that's about 4.36. So hopefully you can see that's exactly what is happening in this case. So again, I just wanted to be clear. I just wanted to be crystal clear about what is happening in these RC circuits and how well they work as a timing circuit. And that's it.